Intro music. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Benjamin Steltner with us today. Hey, Benjamin.
Hello, Frank.
How are you today?
I'm very fine. The sun is shining, blue sky. Finally, spring has arrived.
Awesome. Awesome. And what's your geolocation?
I'm in Hannover in Germany.
Oh, okay. Yep. Very good. I'm here in Phoenix, Arizona. So it's my morning. It's your late afternoon.
Late up, yeah.
But it's good to hear spring has finally come.
Yeah, after a long winter, finally sun is coming out and it's getting warmer.
Yeah.
Really enjoying going outside.
Yeah. So the trees and flowers are coming up and budding.
Yes.
Awesome.
Yeah.
Very cool. Very cool. So what is your position there in Hanover?
I'm a PhD student in the last year, hopefully. Let's see.
Congratulations.
Thank you. And I'm at the Albert Einstein Institute in Hanover. Mm-hmm. So for gravitational physics.
Cool. And when do you anticipate graduating?
Within the next year, so maybe end of this year, start of next year. Let's see.
Okay. Awesome. Awesome. Dr. Steltner.
Soon to be, hopefully. Yeah.
That was very good. Very cool. Can't tell because of your fuzzy background, but are you guys back in the offices? Or are you still working from home? Or
no, I'm still at home since last March. Actually, yeah. I think I was 3 times in the office. Once to water the flowers, then the week afterwards to get the flowers home because I couldn't bother to water them all the time. Right. And the third time was the defense of a colleague, and that's the only time I was on the office. And yeah, otherwise enjoying the home office more or less.
Hopefully you go back before you graduate.
Yeah. Yeah, I would rather prefer a graduation in personal and not via Zoom or something else.
Yeah, very cool. Cool. So Benjamin, what do you like to do for research?
I like noise, finding stuff in noise, the needle in the haystack or multiple needles. I find it very interesting to really dig into it, look what it does and what it hides.
Cool. Cool. Very cool. And that is going to bring us to this really lovely article.
Thank you.
Yeah, this one caught my eye. Einstein at home. All skies search for continuous gravitational waves in LIGO O2 public data. And Benjamin, take us away.
Thank you. Yeah, we should start with dissecting the title a bit. Continuous gravitational waves are nearly monochromatic gravitational waves, which are emitted on a long time scale. Most promising sources for these are fast-spinning, non-axisymmetric neutron stars, which feature a tiny bump, which we like to call a mountain, of course exaggerated, on it. And while the neutron star spins, it continuously emits continuous waves. And in principle, these are kind of boring signals, sinusoidal. I mean, if the neutron star spins down, then the frequency spins down a bit as well. And since we are on Earth and we are rotating around Earth and around the sun, the signal gets a Doppler modulation, depending on where from the sky it comes from. So we didn't detect a continuous wave yet, because mostly due to the reason that these are weaker than the CBC. So if black hole and black hole, or black hole and neutron star, etc., merge together, that they are much louder.
Right.
On the strain amplitude order of 10 to the minus 21 or so, and continuous waves are expected at minus 26 or lower. Okay. Really. And the only way we can detect them is to integrate long durations of data. which is nice that we can do this and build up the SNR, but that is also very expensive computationally.
Right. Cool.
And that depends on the target we have. If we have, for example, the pulsar, which we know by EM measurements, we know the sky location, we know the frequency and the evolution. That's a rather inexpensive search. But if we only target, for example, a supernova remnant, we only know the sky location, then of course we have to search over the frequencies. And if we have no target information, do a blind search or an all-sky search, we search all over the sky, therefore have for every sky position a different waveform. And then this really becomes very expensive.
Mm-hmm.
And that's where Einstein at Home then comes into play, which is I always get the order wrong. Volunteer distributed computing project. Right. So where volunteers can spend their idle computational resources, be it a laptop, a big beefy computer, or even a smartphone, can spend it to advance our science case, which is really nice. Yeah.
Very nice. Mm-hmm.
So that was the title. Oh no, I forgot. Yeah, we used for this paper the advanced LIGO data of the second observation run, the public data, which you can just download. Yeah. Maybe let's go to figure 1, I think it is.
Okay. The signal. Figure 1.
Yeah. The O2 data, or the O2 observation run, lasted for roughly 9 months. Due to data quality issues, we started a bit late in January, and therefore had like 7.5 months of data, which is really a long time scale. Mm. We usually prepare them in so-called SFTs, short Fourier transforms, and these are the 2 lower bars. You can see a few gaps where there's a commissioning break. There was something at LIGO Hanford which was excluded. And at the end, the tiny break, I find it really interesting, was the earthquake in Montana, which kicked both detectors out of sync. So we used, in total, I think it's like if you put it continuously, 3.5 months of data, which is kind of quite a lot. And we are using a search technique called matched filtering because our signals are so deeply buried into the noise. And this matched filtering really lets us find these signals. We employ 2 detection statistics. That's the F statistic. Maybe zoom out a little bit. I think it's section 3. So in this page, where we with the F statistic so simply speaking, we put in the waveforms, and then the F statistic tells us if it's likely signal plus Gaussian noise, or if it's only Gaussian noise. Since we have to, Let
me ask a question on figure 1. Why is stage 8 covering the full range and all the others are broken up? I understand why they're broken up from the below, but why is stage 8 all the way across?
Actually, stage 8 only begins at the start and ends at the end. Yeah. And in principle, there are these gaps, so we didn't magically come up with more data. But it's just that the segment started at this time and ended at the last time. I mean, we could have put like these double brackets to indicate that there's a gap and that the segment moves on, but I think that would have cluttered the image a bit.
Got it. Okay.
But good. Valid point. We didn't come up with more data on the spot.
Got it. I'm good.
Yeah. Okay. So since we have so much data and we basically, brute force each waveform, a coherent search over the whole observation time is computationally prohibitive. So therefore we employ a semi-coherent search scheme where we divide the whole observation time in different segments. And these segments are, in figure 1, the vertical bars show the start and the end of a segment. And then we do the coherent search on each segment, and then build the detection statistic by averaging over all the different segments.
Okay.
So in stage 0, the initial stage, there were 64 segments. So we did a coherent search on all these 64, and then summed them up.
Got it.
Yeah. To the later stages, we will come in the later part.
I see what's going on. Okay, got it. I'm with you.
Yeah. So the unfortunate thing, so we all love the statistic, it's great, but an unfortunate thing is that it's only gets the likelihood ratio of the data containing the signal waveform plus Gaussian noise versus Gaussian noise. And there are things in the LIGO detector due to instrumental or environmental disturbances where the statistic then basically says, this doesn't really look like a signal plus Gaussian noise, but it does look less like Gaussian noise. So the detection statistic value gets a bit elevated. And therefore, we use a second detection statistic, which is the line and transient line robust statistic, which is really a mouthful, which is, as the name suggests, a bit more robust against these, a bit more down. Yeah, on the left side, the ESGLTL, which is a bit more robust against these disturbances, where it's not only testing signal plus Gaussian noise against Gaussian noise, but against lines and transient lines, so only short lines, and therefore suppresses most of the noise as well. Really good. Cool.
Okay.
Yeah.
Cool.
So that's how we search. And I mentioned it in the beginning. It's very computationally expensive. And therefore we have to make sure that we don't do anything stupid and really manage our resources well. Since the Einstein at Home all-sky searches usually last like half a month on Einstein at Home. So the volunteer, not each individual volunteer, but overall are calculating half a month. So it's important that this half a month is spent with the best setup of the search we can get, and not something which, we could have chosen a better one, and when this only takes 1 month or so. So we put really much thought into the search grids, how we make them, because we are using discrete template grids, so we always have a mismatch between the signal waveform and the discrete template grids. Because usually the template grid does not fall onto a signal.
Right. Okay.
And that's, in principle, one can do it analytically. But unfortunately, in reality, that doesn't really hold because of some assumptions. So we always do it with the Monte Carlo studies with injections and see for selection of different search grids, what the actual mismatch is like. So what is our fractional signal loss? And for the initial stage, because it's so expensive, it's still 50%. So on average, 50% of our signal is lost.
Wow.
Yeah.
Okay. Let me ask a question. How many volunteers do you have at Einstein at Home, roughly? 100?
That's always a very good question, because sometimes they go and come.
Yeah.
Is
it 1,000? Is it 1,000,000?
I think it's on the order of 10,000 or so.
10,000, okay.
I think. Yeah. Where was I? The Monte Carlos.
Yep.
So we make sure that we really are at an optimal point, given the computational budget we have, which really isn't that easy to calculate because, as I said, you can basically throw everything into Einstein at home, and then it makes a difference if you have a really good PC or a not so good PC in our runtime estimations. That's hard to predict.
Yes.
But usually it matches quite well. Yeah.
Cool.
Maybe a bit down.
Oh, here we go. Overview of the searches.
Yeah. So in total, we searched 7.9 times 10 to the 17 waveforms, which I always forget what number. It's something like a million, billion or so. I think it still has a name, a number name. Ooh. But it's like you never use it.
I can go to 12. I can go to powers of 12, right?
Yeah, and afterwards it's like, okay, it's 10 to the
well, I guess
many
exa
zeros.
would be 10 to the 15. So it's like 100 exa something. Oh. Very good. Okay, 10 to the 17. I like that better.
Yeah. Yeah. And that's the whole. So these 10 to the 17 waveforms or parameters are split into 8 million work units, where one work unit gets sent to the volunteer, and the volunteer on average calculates roughly 8 hours on one work unit. Mm-hmm. So we are very, very happy to have Einstein at home, because otherwise we would wait for like 10,000 CPU years until our computations end. And who has so much time? Yeah.
Before they graduate.
Yeah. Ooh. Each work unit roughly calculates over 100 billion templates, which covers 50 millihertz and the entire spin down range and small portion of the sky. But we only return the loudest 7,500 results of all these 100 billion different waveforms. Okay. And we always call them loudest, with which we mean the candidates with the highest detection statistic values, which is ranked by this BSG LTLR. Right. The line and transient line robust statistic, because that really suppresses noise very well. So our results are quite sparse, not only in the waveforms we search, and after all, we have like 8 million times 7,500 is something like 60 billion candidates back at home, then on our server. Yep. Where then the post-processing starts. Where we first, of course, have to put all the different work units together, all the different sky positions. Then we do some identification of disturbed bands, where one sees by eye that something looks strange. We still process these bands, but in the end, for setting our upper limits or results, we can't really say, okay, we can't exclude anything in there because it's so much noise, which again is very interesting to see how it's what it's hiding. Yeah, I think in a previous paper, so the 01 Einstein at home all-sky search, there was the sentence: a scientist looks through the images and identifies disturbed bands. Which I find very prosaic. Yes. Because it really means you sit there like half a day looking at thousands of images. Right. And just we have a little GUI tool where you can then say, okay, next image and disturb, not disturb, and etc. And then to sit there mostly with the coffee and then next one and be the little machine Yeah.
Very cool.
Yeah. And after, yeah. And afterwards, we do a very important step, which is called clustering. Since with 60 billion candidates, it's still hard to do anything. So there are so many. But the good thing is that due to the way that how our template grids are set up, these are not independent templates, but we have like slight overlap to reduce the mismatch. So if signal or disturbance triggers one parameter, it is highly likely that the parameter right next to it is elevated as well. And therefore, yeah, correct. And therefore, we try to find all the candidates which are from the same root cause, be it a signal or disturbance, and then group and find them, cluster them, and then pick out the one most representative seed of all of them and continue only with them. And in fact, our results are so sparse that something signal-like or disturbance-like produces multiple candidates, but there are really many which just are single candidates. And with this, we, again, based on Monte Carlo studies with injections, found that all the signals we can find have at least at least 3 companions. So there are 4 in total. And therefore, we could reject anything which had less, so was single or only double. And that made it possible to go from 60 billion to only 350,000 candidates.
Yeah.
Which is a number which is, yeah, one can handle a bit more. And with these 350,145, we then went into a hierarchical follow-up. I like this word, hierarchical follow-up, where we followed them up in 8 stages, where in each stage we increased the signal-to-noise ratio.
Here we go. Okay.
Yeah.
Yep.
So we can do this by 2 means. Maybe let's go back to figure 1.
Yes, now this is becoming much clearer to me now. Okay.
Yeah, so we can do this in 2 means to increase the SNR in each stage. One is increasing the coherent time, so making the segments larger. This we did from stage 1 to 2 and 3 and afterwards. Up until in stage 8, we are at a fully coherent search. And the second method to increase the SNR is, of course, to go to a finer grid, which reduces the mismatch between the signal waveform and the discrete template grid, which we did as well in each succinct stage. That's table 1, I think, yeah.
Yeah. Table 1? Yep, right.
Yeah, it's a very long table. Yeah, in the second column, we see again the increase in the coherence time, where we roughly doubled it always up until the last stage, where we went the 5,486 hours, so the fully coherent search. And the mismatch is 1, 2, 3, 4, 5, 6. The average mu. So in stage 0, we had a mismatch of 50%. So 50% of the signal power was lost. And we gradually reduced this up until a fraction of a percent in mismatch, where we had really fine grids. Yeah.
Right. I'm with you. Yep.
Yeah, and of course, if both of these, so increasing the coherence time and the finer mismatch or the finer grid, increases the runtime. So that becomes only possible by reducing the number of candidates.
Yep.
So we need to come up with some measure to reject candidates, which we did with this R threshold. I think it's a bit low. Yeah, exactly. That's the value. That's basically the SNR of any candidate at stage A has to improve by this factor compared to stage 0. And since stage 1 was only a refinement in Sky, actually the signal strength could, or the SNR of the candidate could actually decrease to 75%, but afterwards in each stage it had to increase up until into the last stage where the SNR had to increase by a factor of 50 compared to stage 0.
Right.
Yeah.
Yep. Okay.
And yeah. Okay. And since we are going to more coherent, so longer coherent time segments, and noise is usually incoherent, it does not, or noise does not increase as much as real signals or our injections, which again in Monte Carlo studies of injections where we derived this threshold. And then in the last two columns, you can see that of the initial 350,000 candidates which we went into the follow-up, where stage 0 is the Einstein at home search, so on the volunteers, and stage 1 to 8 we did on the cluster at home, so to speak. That's the Atlas cluster. We could reject a good portion of candidates in each stage up until the last stage, where only 6 surviving candidates were. But unfortunately or not, these were all the hardware injections which LIGO put into the data, which were in our search range. So there are multiple hardware injections, which happen, as the name suggests, on hardware in the detectors, where they simulate or actually inject the injections onto the mirror. So everything which happens with the data acquisition and calibration, etc., is equally applied to these hardware injections, and they are really a good test if we did everything correct. And indeed, there are only these 6 in our search parameter range, and we did find all of them. Good. And if you look then at the recovery of them, they were really precise. So I think in frequency it was on the nanohertz differences of stage 8 candidates to the actual hardware injection parameters, and something like 10 to the minus 15 hertz per second in spin down. And in Sky, it was like if you stand on Earth and look at Pluto and Neptune, that's roughly the same ballpark. Okay. So that was really a good test for us to see that we indeed find everything which there is. But unfortunately, we didn't detect a continuous wave. So no outliers to look at. But based on our non-findings, we could still set upper limits. So what can we exclude? What neutron star mountains of given sizes and distances could we or would we have seen? I skipped a few figures here. Yeah.
If you want to go through them, it's fine.
Yeah, sure. A bit more. Yeah, correct. So the two left panels are. I got too carried away by the table. It was so precise and led to the 6 candidates. Yeah. That the two left panels are what happens if we look at the loudest candidates in the 2 detection statistics in 50 millihertz bands. 50 millihertz bands are usually our tiniest thing we look at, because otherwise the amount of data is just too huge. And there you see that we have 3 colors. The blue one are undisturbed bands, and the red one are disturbed bands, which is again based on these visual inspection, what we did. And as you can see, the disturbed bands are not always, but often quite high, as well as in the 2FR, as in the BSG-LTLR, so the line and transient line robust statistic. And there are these green squares, which are the hardware injections, which are kind of loud. While the line and transient line robust statistic is very good at suppressing noise, it's a bit cumbersome to work with it. And the 2F, so the F statistic is a bit more easy since that follows a chi-square distribution. Where you then calculate what's based on the number of templates is the expected loudest in these 50 megahertz bands, which is shown in the lower plot in the what is it, orange area, with the crosses. So it's a bit hard to see, but apart from the disturbed bands, our results fall right into what we would expect in Gaussian noise. And the right two panels are what actually the 350,000 seeds look like in frequency versus these two detection statistics. And if you compare these two left and right plots with each other, in F statistic, one does not see that much because of the scaling, but in BSG-LTLR, one really sees how deep we dig into the noise. Maybe because it might be confusing, the line and transient line robust statistic can be negative. So that's the symmetric log on the y-axis. So it's logarithmic from 10 to above, and downwards it's linear.
Okay. I'm with you. Okay, tricky.
But I think these plots are really, really nice to see what kind of candidates we really look at and how much deeper we dig into the noise instead of just taking the loudest and go with it. But the clustering method really looks into detail up to lower levels in the noise. The next figure is basically just the mismatch, so signal power loss in the different stages. I think it's quite beautiful, but maybe less clear than the table.
It's a beautiful plot.
I like the colors.
I like the use of. There's a good use of transparency, alpha channel. It's nice. Good.
Probably took like 50% all the images, like always, like 50% of writing the paper is fiddling around with the images and then getting the scaling right and the horrible legend.
Yes. Beautiful plots take time. Very cool.
Okay, then a bit more down.
Ooh, that one I like. Okay. Two important ones here.
So the left plot basically shows this R threshold again, how much the candidates or the signals have to improve in their SNR throughout the different stages. And these are the candidates we have are the bars which are filled. And our Monte Carlo simulations with the injections are is it a step function or a bar with no filling?
Right.
And the threshold is then the vertical line, which is dash dotted.
Right. Right.
And then finally, the hardware injections are the filled bar with the stripes out of it.
Very good.
And as you can see, in the beginning, these two distributions overlapped. And we had to increase the SNR by the two means. So increase in TICO and the finite grid. And then at around stage 3 or 4 or 5 or so, then really these two distributions were splitting, and we could reject many candidates up until in the last stage. There were the two candidates on the left side, which did not increase enough. And at the right side, the 6 hardware injections, which did survive this threshold.
Right.
And then led to our results that we only could recover the 6 hardware injections. And afterwards, we looked, of course, into the last few candidates which we rejected. I mean, one should always look at what candidates one rejects, and these were then we find out remaining lines which we didn't clean or which we didn't saw before in the both LIGO detectors, and therefore they made it up until the end.
Yes.
Where then the search resolution was too small, so we could finally reject them.
Cool.
And so then we can go to the upper limits based on our non-finding. We did extensive studies. Again, what kind of signal amplitude would we find with our setup, and what do we not find? And we do this on the 90% confidence level.
Okay.
And these upper limits then hold true, or are true for population average. So over the parameter space, so all sky and the spin down range. Yeah, we are the black curve.
Mm-hmm. Yep.
And we do the population average over the inclination, antipolarization, etc. Yeah, we did improve compared to existing all sky searches. That's the upper one are the lower one, gray shaded ones are the frequency half. In between is time domain, and the upper one is sky half. I don't know. So the LIGO results, and our search was complementary with the what color is this? Coffee color.
Yep.
That's the Falcon search, which is at higher frequencies and probes smaller ellipticities, yes. Where our search had a quite broad spin down range. So that's really the breadth and the depth search, so to speak. Yeah.
Mm-hmm. Yep.
Yeah. We have a few discarded or discarded. So we do not set upper limits in a few bands, which are half hertz or 50 millihertz, which are either disturbed by the visual inspection, or where we do some frequency cleaning to get rid of the most of astrophysical lines in the detectors. And in those bands, we couldn't then reach the 90% upper limits. And the bands and the upper limits we give in the machine readable supplemental in the paper.
Mm-hmm.
So
okay.
Yeah, and then based on the upper limits, one could look at the ellipticity. So actually, what kind of mountains would we have seen, or can we reject the mountain? It's defined as the ellipticity of a triaxial ellipsoid, yes. As equation 9. And tells you how much the neutron star can deviate from the perfect rotational ellipsoid. Uh-huh. And so in figure 7, we have the ellipticity at different distances. So 50 parsecs, that's so like neighborhood. And up until to 8 kiloparsecs.
Okay.
And so for signal frequencies, I think at above 250 hertz. So rotational frequencies of 125 hertz, since it's always double, we can reject neutron stars with an ellipticity of 10 to the minus 7 or so.
Yes.
Yeah, for 50 parsecs. Yeah.
Yep. Yep.
And at 100 parsecs or so, it's I think above 400 hertz signal frequency, so 200 hertz rotational frequency.
Yeah. Okay.
Yeah.
Yep.
Yeah. And these are ellipticities which could be present on a neutron star, although that really is still open research, how these mountains can be produced, how they can be sustained. So how long can they be there? I mean, that's important as well. For us, they should be there all the time of the observation run.
Right.
Otherwise, you have another kind of CW research where you look for transient signals, which opens just another box of worms. So that's really, really interesting. But yeah.
Cool.
Yeah, that's the main result of the paper. Yeah.
Very nice. Thank you, Benjamin. Thank you for walking.
Thank you for having me.
Really lovely article. So you hinted at it a little bit there at the end of the article, but where do we go from here? Let's say over the next 4 or 5 years. Presumably, you're going to do a similar analysis for 03, 04. Yeah. So where do we go?
Yeah. So I think last Saturday, LIGO broke the news that the 03A data release will be imminent on 30th of April this year. So that certainly will be another point that we use this data, and at some point then the 03B as well. Yeah, and as you mentioned, as always, if there's new data which dramatically increased or improved in performance or in sensitivity, which is really nice, one can probe deeper and deeper. And with continuous waves, the nice thing is that if we have some more candidates, we can even go back to the data and look for these candidates there. Of course, it's always a bit difficult with these sensitivities. And if this mountain is sustained for such a long time. And the main prospect, I think, for in 5 years is probably finding a continuous wave. And then we can sort of start with the physics, how these mountains can be generated or sustained, and what can be learned about the equation of states of neutron stars. So that will be very interesting, and we hope for the best.
Let me ask, more compute is always nice, but what if you had 10 times as many volunteers on Einstein at home? Does that increase the amount of science that one drives out, or?
Certainly. I just now forgot how our sensitivity scales with the computational power. I think it's something with the root in it. So it's not it's not like if there's 10 times more that we gain 10 times more, but it would certainly help. Even root of 10 is still good, so we would take that. Yeah.
Okay. I'm just looking to give a little PR to people who might be watching to volunteer your cycles to Einstein at home. Be great. Yeah. Very cool. All right, that'll do. Benjamin, thank you very much again for walking us through your lovely paper. And
thank you, Frank.
Everyone, we will see you on the next one. Bye-bye.
Bye.